example 4. This is an example that is now so complicated that I don't even want to try to do it the long way. This looks no fun to do the long way at all. So I'm just going to guess the answer. And I'm going to show you how we can just write down the answer. So the idea here is when you have a system of objects, the acceleration of the system equals the total external force on the system. You ignore internal forces like tension and normal forces, divided by the total mass of the system. And the way to think about this sum of the forces is that you have some positive forces those positive forces make the system go. And you have negative forces that slow the system down. And you divide all that stuff by the total mass. So let's see if we can do that for this example. Let's think about what's happening in this picture. We've got 3 objects, 3 masses. They're connected with ropes over pulleys. Mass 3 is just going vertically. That's the simplest one. Mass 2 is on the slope of angle theta 1. It's experiencing a friction force with coefficient mu k1. Mass 2 is on another slope, angle theta 2, with its own coefficient of friction, mu k2. So there's a lot going on here. But let's assume that the system is moving this way. Mass 1 is moving up the slope, mass 2 is moving down its slope, mass 3 is moving down. If that's the case, then the forces that make things speed up would be the gravity force pulling on mass 3, and the gravity force on mass 2 along the slope. Now there's several things slowing the system down, so those are all going to be negative. We have, first of all, the gravity force on mass 1 along the slope. And we also have these 2 friction forces. Divided by the total mass, which is m1 plus, actually let me write that in words first. We'll do symbols in the next step. Okay, so I've just identified in words what's going on here. And I hope that's sensible. I hope you can look at a problem like this now and at least think in very broad terms what's going on like this. And now what we can do is we can plug in the formulas for each of these things because we know how to do all those. Those are all smaller problems we've done in the past. So let me replace each of those things that I wrote in words with the formula that we've already learned how to do from previous problems. The gravity force on M3, because it's moving straight down, is going to be M3G. That's easy. The gravity along the slope on M2, well, we've learned that when you do slope problems, the gravity force along the slope is mg sine theta. You can go consult previous slope problems we've done to see where that comes from. Next, gravity along the slope for M1, that gets subtracted. It's that same formula. Friction force on M1. Well, in slope problems, we've seen that friction force on the slope is coefficient times mg cosine theta. The cosine comes from the normal force, remember. So friction on 1 would be the coefficient for 1, m1g cos theta 1, and we do the same thing for mass 2. Friction force coefficient m2g cos theta 2. And all of that is divided by the total mass, m1 plus m2 plus m3. So that's how we can quickly find the acceleration of a system of connected objects, even when it's something really complicated looking like this. You just think in broad strokes about what's going on. You can even write it in words, and then replace all of these parts with the formulas that you've already learned from having done lots of problems before.